Hello team! So today we're going to be looking at key features of polynomials. All right, so for the past few lessons, we've been working with polynomials, and let's see what new stuff we can learn about polynomials. All right, so here we have a function y equals x plus 2 times x plus 1 times x minus 2, right? And the first thing that we want to find is 0, like our zeros, right? And we can find our zeros by looking at the intersection of our graph with the x-axis, right? So here I can tell that, hey, -2, at -2, -1, and 2, my function is touching our x-axis, right? So I know that my zeros are at -2, -1, and 2, because that's the point of my graph, or those are my points of the graph touching the x-axis, right? Y-intercept is the other way around. We can find y-intercept by looking at when our function touches the y-axis, meaning when x equals 0, right? So we're going to find this point. Let's find that point. In this graph, I know that this point exists at -4 when y equals -4 and x equals 0. So we've been finding zeros and y-intercepts for quite a few years at this point, right? So this is review. The new things that we're learning today are turning points and end behavior. So we're going to look at what turning points are, right? So what does local minimums and maximums really mean, right? Local minimums and maximums can be also called as regional minimums or maximums, and we will see. So local meaning around this area, our point is either the highest, the maximum, or the lowest, which is the minimum, right? So let's look at what we have here, right? So at this box, let's draw this box. We're looking at this zone because we see a point that's very high, right? So in this region, I can say, hey, this point is the highest point around this area, right? It's the highest point around this area. That's why it could be a local maximum. So this is our local maximum, right? And this point exists at x when x is -1.5 and when our y is at 1, right? So in this region or around this area, I know that this point, -1.5 and 1, is the highest. So this satisfies for a local maximum. And let's try to find a local minimum of this graph. So a low point of this graph, let's just circle this region, right? The lowest point of this region should be at this point, right? Because we don't have any point that's below this, right? This is the lowest point of our graph. And this point is at when x is 1 and y is -6. So we can say 1 and -6 is my local or regional minimum. All right, I hope this makes sense. If not, let me know. All right. And end behavior, on the other hand, is the other new thing that we're learning today. And end behavior defines the graph when x is either getting really, really, really big or really, really small. So let's write it out. So it means, let's choose a color, let's use brown. End behavior defines the graph as x gets either really small or really big. Okay, We're going to see exactly what that means, right? When x gets really, really big, how do I know when x gets really, really big, right? Take a minute and pause. How can I know when x gets really big, right? So up within this graph, I only see when x is at 3, right? So when x gets really, really big, it means it can reach infinity. So it's going really, really to the right, right? So when x gets really far to the right, what happens to my function? So we're going to be looking at the direction of this. So we can see that approaching 2, we're moving upward. So we know that, hey, this function will continue going upward even when x gets very far to the right. So when x gets really far to the right, when x approaches infinity, our y function also approaches infinity because we are continuing moving upward, right? And on the other hand, when x reaches negative infinity, it just means that we're going very far to the left, right? A very, very big negative number, like negative, like billions, right? Like really big number. And let's look at the projection of our y function. So our y function is moving downward, right? So it means that even when our x value gets super, super far left, our y function is still going downward. So it means that when x is approaching negative infinity, our y function is also approaching negative infinity. Yeah, that's just how you can explain this graph and how you can find the zeros, y-intercept, turning points, and end behavior of this example. Okay, let's look at our second example. Second example asks us to match the letters with the correct terms, right? So remember, for zeros, we need to find where our where our function touches the x-intercepts, right? The x-intercepts is right here. So I see at A and D, I touch the function touches the x-intercept, right? The y-intercept, on the other hand, is the other way around. It's when x equals 0, and we're solely looking at where our function is touching the y-intercept, right? So we see here that, hey, our y-intercept is at C, right? It's like what? 0, negative 0.5, right? Our maximums, right? Okay, our maximums, we only have one maximum in this case, right? Right here. The only high point of our region of this squiggly graph, right, is here at E, right? You can see compared to other points within within other points in this region, this is the highest point that I can see, right? That's why our E is the local maximum. Okay, so because F is right next to E, let's just look at F, right? So in this same region, I can see that, hey, oh my goodness, hey, in this region, I can tell that, hey, I'm the lowest around those points, right? That's why I know that, hey, I am a local minimum. And the last here we have B. Similar to F, B is the lowest point around the points of that region. So you have points here, 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 here. And B is the lowest point of this region. So B is our regional or local minimum. Okay, we're almost there. We're looking at our end behavior. Remember, our end behavior is when x approaches infinity, meaning it's going very far right, we want to look at the projection of our y function. So our y function is going upward. So it means that even when x is going very, very far to the right, our function is continuing going upward. That means that when x approaches infinity, our y also approaches infinity. It's a very, very large number, right? And let's look at the other way around. When x is approaching negative infinity, meaning it's going very far to the left, our y function is still here. It's not still here, it's here going upward as well, right? So it means that even though when x is approaching negative infinity, going very far to the left, we are moving upward on the left side of our function. The left end of the function is still going upward, right? So when x is approaching negative infinity, our y is approaching infinity, right? So a common question I have is like, hey, miss, shouldn't we have a negative infinity and a positive infinity for our y? No, you can have two negative infinities and two positive infinities, two infinities. It doesn't really matter. All that matters is what direction are the ends of my function, right? Oh, the lag. Let me pause a little bit. So I don't need to always have a positive and negative. All I'm looking at is what the end of my function is telling me, right? Okay, let's look at our last example. Let me erase the ends so we don't get distracted. So this is our last example. Y equals 0.4 times x plus 3 times x minus 2 times x minus 3, right? So I think our first step is still finding our zeros, right? Let's find our zeros, which is just any points on this line, right? So I see it's at -3, 2, and 3, right? -3, 2, and 3. And my y-intercept is any point or points touching this line, right? This line. So I have 7, right? I have this point 7. This point 7, right? This can also be written as 0, 0, 7. And let's find our maximums. Do I have multiple maximums? No. For this case, I only have one maximum, right? At this point, because it's the highest of my region. So right here, this point is the highest point of this region, right? Around this part. And so it's at, -1 and 9.5. So it's at -1, 9.5. If you remember when we did quadratic formula, we talked about parabola. You know, parabolas are this, right? Or this. Remember this thing we called a vertex? Vertex is either the highest point of the lowest point or the lowest point. So usually if you can find the vertex of a region, that's your local maximum or minimum. Okay, that's just helping you remember, if you remember what vertex are. Okay, let's find our minimums. Do I have multiple minimums? Nah, I only have one, right, in this area. So I know that, hey, at this point, it's the lowest point of my graph, right? Of all those points, this point is the lowest point. And this is at -0.5 and 2.5. So 0.5, -0.5 is the y, right? So our x is still 2.5. Always write your x first, unless told otherwise, and -0.5 for your y. So that's our minimum. The last step is to find the end behavior. The end behavior when x is approaching infinity, right? Let's look at the projection of our graph. Okay, so it's showing that, hey, my graph, my y function is going upward, right? So when x is going far right, my function is still going upward, meaning it's approaching infinity. right? And let's look at when it's going far left, right? Far left meaning, hey, my x is going or approaching negative infinity. Let's look at the end of the left side of our polynomial. So the last end that we see in the graph or in this window is that it's going downward. So we know that even as we approach very, very far to the left, my polynomial is still going downward. This means that our y is approaching negative infinity as x is approaching negative infinity. And that's how you find your zeros, your y-intercept, your local maximums, local minimums, and end behavior.